Okay, so this is a recording of the first half of class for Friday, February 11th. And today's class is all about Bitwise Ops. Bitwise operations in the C programming language. So how do we manipulate bits in the C programming language? So let's start with a classic example of AND. What if I want to do an AND operation? And what I mean is, let's suppose I have an operand that looks like this, 0, 1, 1, 0, and 1, 1, 0, 1. And I want to do a bitwise AND with another operand that is 1, 1, 0, 1, 1, 0, 1, 1. And I'm going to write the bitwise operand as an ampersand. That's my ampersand, sorry, it's really messy. And I'm going to go column by column. So in the first column over here in the rightmost, I have 1 and 1, and the result is a 1. I have in the second column 0, 1, and the result is a 0. 1 and 0 is a 0, this is a 1, this is a 0, this is a 0, this is a 1, and this is a 0. So there is my result of a bitwise operation. And you might be asking, why would you want to do such a thing? Why do you care about bitwise manipulations in something like this? And here's the reason. Let's suppose I have some kind of generic byte quantity that is 7 bits, or 8 bits, sorry. So B7, B6, B5, B4, B3, B2, B1, and B0. And let's suppose that I want to do an AND operation right here with something that's on the bottom. I'm not specifying what it is yet. And the result that I want to get is I want certain bits to be cleared. I want them to be set to 0. So for example, let's suppose it's B0. I want to make sure that the result is B0 equals 0. And let's suppose B3 is also 0 and B4 is also 0. And then I want the other bits to stay the same. So B1, B2, B5, B6, and B7. So this kind of operation allows me to selectively clear certain bits. When I say clear, I mean change to a 0. And here's how I'm going to do it. I'm going to put a 0 in the location of where I want the zeros to go, right here in my second operand. Because no matter what value B0 is, when I AND it with a 0, I'm going to get a 0 result. And the same thing is true with B3 and B4. No matter what values those are, when I AND them with a 0, I'm going to get a 0 result. Now, in these other locations, I'll put 1s. And when I AND B1 with a 1, it stays the same. If it was a 1 before, it stays a 1. And if it was a 0 before, it stays a 0. So when I put a 1 in these other locations, it retains the value from these other bits. This principle is called an AND mask. And it allows us to select bits to clear. That means change to 0. And we're going to use a 0 in the mask in the location of where I want to change the bits to clear, where I want to clear the bits, if you will. So that's a good operation. That's a good idea of why you might want to use an AND mask. So for example, in my C code that we did the other day when I did my print char function, right, I used an AND mask of 1, and that puts a 1 in this location and zeros everywhere else. And it has the effect of clearing all the bits out and just retaining whatever bit this is. And so it allows me to retain the rightmost bit with an AND mask of 1. So if you go back and look at the code, you'll see that there's an AND of 1 there, and that's the result of retaining that rightmost bit and clearing all the other bits out. We can do the same kind of thing with an OR mask too. So let's take a look at a classic OR operation. So 1, 1, 0, 1, 0, 1, 0, 0, and I'm going to OR 0, 1, 0, 1, 0, 1, 1, 0 right here. And I'm going to OR these two things together. And in C, the OR operator is a vertical bar. So I'm going to put it over there. It looks like a 1, but it's a vertical bar. Okay, so bitwise OR, the first column, 0, 0, gives me a 0. 0 or 1 gives me a 1. 1 or 1 gives me a 1. This gives me a 0. This gives me a 1. This gives me a 0. This gives me a 1. This gives me a 1. So going column by column, bitwise ORs allows me to get that result. Now, if I want to use a bitwise OR mask, let's think again generically about some 8 8-bit quantity, a byte quantity, B7, B6, B5, B4, B3, B2, B1, B0. And let's suppose that I desire to have a result where some of the locations are set to 1. Let's pick these same 3 bits. So 1, 1, 1, and otherwise I want this to be B1, I want this to stay as B2, I want this to be B5, I want this to be B6, and I want this to be B7. So some of the bits remain unchanged, and some of the bits are set to 1. With my OR mask, what I'm going to do is I'm going to put a 1 in these locations where I want to set a 1, because when I OR B0 with a 1, it's always going to be a 1, no matter what B0 is. Same thing with B3 and B4. In these other locations, I'll put zeros, and that keeps those bits unchanged. B0 stays the same value it was before. If it was a 0 before, it stays a 0. If it was a 1 before, it stays a 1. So those bits remain unchanged where there are zeros. So we have over here our OR mask, if you will. We can select bits to set. In the places where we want to do the setting, we're going to change to a 1. So we use a mask with a 1 in the places where we want to do the setting, and we use zeros in the places where we want to leave the bits unchanged. So between the AND mask, which allows us to clear some bits, and the OR mask, which allows us to set some bits, we can do some pretty good operations. There is also an exclusive OR. And real quickly, we'll just do a quick example. And I'll do an exclusive OR. In C, the exclusive OR operator is the caret symbol. And so remember, exclusive OR 1 is a 0, this is a 0, this is a 1, this is a 0, this is a 1, 1, 0, 0. So exclusive OR, one of the 2 bits has to be a 1, and one of them has to be a 0. Okay, so why would you use an exclusive OR? Well, an exclusive OR allows us to do a selective bit flip. And we will use a 1 in the location where we want to do the flipping. So let's see how this works. So again, if I just have some operand here that is 8 bits, and I want to do some kind of exclusive OR mask right here, and I want the result of this to be a complement. So I want this to be B0 bar, I want this one to be B3 bar, and I want this one to be B4 bar. I want those things to be changed, and I want the other bits to stay the same. Well, in those locations then, where I want the changes to happen, I'm going to put a 1 for my mask, because a 1 will cause the value to be changed. Remember, a 1, 1 goes to 0, and a 1, 0 goes to 1. So if B0 is a 0, this goes to a 1, and if B0 is a 1, this goes to a 0. In these other locations, I'll put zeros, and when I do exclusive ORs with the zeros, the bits remain unchanged. So this allows me to make a mask that will flip certain bits, and I can pick which bits I want to flip by putting 1s in the locations where I want to do the flipping. So that's pretty cool. All right, some other operations. Some other operations that we can do is we can do what's called a Bitwise Not. And this is different than a logical not. So let's not get confused with a logical not for a second. The logical not operator in C is the exclamation point. Over here, we're going to be talking about the caret symbol, which is the bitwise not. And so in the bitwise not, if I have 1, 0, 0, 1, 0, 1, 1, 1, and I do a bitwise not operator in front of this, then what that's going to do is it's going to flip every single bit. So it's like a 1's complement, if you will. So that gives me 0, 1, 1, 0, 1, 0, 0, 0. That's the result. It flips every single bit. So this is a bitwise not operator. It's kind of like an exclusive OR where the mask is all 1s, right? It flips every single bit. So it's a unary operator. You don't have 2 operands, not a binary operator. It's a unary operator, and it allows you to change all the bits at once, like a 1's complement kind of thing. Now, let's talk about this logical not over here. So important to keep in mind is that in C, there is no real Boolean value. Right? In C explicitly, there's no bool, and in C++, there's something called a bool, but really it's an integer. So in C, they represent Boolean expressions with integer values, and here's how that happens. If it's a 0, then this becomes false. Anything that's a value is interpreted as 0, and if it's not a 0, then it's interpreted as true. So any value that's not 0 will be true, and any value that is 0 will be false. So for example, in C, I'm allowed to do something like this, x equals 3, like this, and then I'm allowed to have a statement if x. Right? And this expression will evaluate to true because the value of x is an integer and it's non-zero. So it's a crazy way of doing things, but that's the way C language does it. Okay, so what happens then if I do this instead? What happens if I do not x, right? Well, literally what happens is I take the value that is x and I see that it is non-zero, so x by itself is true, and then when I add the not operator in front of it, I invert that. So this expression becomes false. So when it becomes false, this expression in totality, the not x, if you will, gets evaluated as a 0 operand. So you can think about it mathematically as a 0. So it changes that value to be a 0. It doesn't change the value of x. It just evaluates that expression to be the numeric value of 0. But that means if I do something like this, if I do x equals not x, right, and I assign the value back into x, well, now x is getting assigned the value of 0. So you'll see the change in there. But it gets even crazier. So let's think about this little bit of code. So if I do x equals 3, and then I do x equals not x, like this, right? This is perfectly legal. This is 2 Boolean nots in front of that x. These are logical nots. So this first logical not here, let's see here. I'm going to undo this. The first logical not right here, this first one, gets evaluated as this is true, so this expression is false, and so that's a value of 0. And now we think about, well, what happens if we have a not 0? Well, this evaluates to true, and C by default picks the value of 1 to be true. So this takes the value of 1 and assigns it back into x. So it's kind of crazy. X goes from a non-zero, which is a 3, to a 0 with the not x, and then the not 0 goes back to a 1, and then you get x equals 1. So that's the way it happens. I want you to know that that's there. You wouldn't normally use that in a program. That's just pretty silly, but sometimes it does actually come up handy, and one of the times that it comes up handy is in systems programming. You wouldn't normally do application programming like this. You would be frowned upon because it's just a weird way to handle numbers. But in systems programming, we like to take shortcuts. And so you might see something like this and it might actually be useful. Okay, 2 more things to talk about. Let's talk about shifting now. So when we talk about shifting, we're going to move the bits in some direction. And we're going to start with a shift to the left. So let's think about what happens when I do a shift to the left. Let's assume I have int x equals 3, right? Let's actually not make that an int. Let's make this a car, unsigned car. So here we go. Unsigned car, like this. So I have unsigned car x equals 3. Well, this is the bit value of 00000011, like this. That's what literally the bits for 3 look like when it's stored as a byte or a car. Okay, so what happens if I do something like this? Y equals x, and I'm going to shift to the left, so I use the double less than, and I'm going to put a 2 over here, and this is going to shift by 2 spots. So I'm going to get a result that looks like the following. Here's my 8-bit result, and I'm going to shift all the bits 2 spots. So this thing comes down here, and it becomes a 1. This comes down here, it becomes a 1. This goes there for 0. 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 And these 2 bits are lost. They're gone. They disappear. And so what happens to these spots over here on the right? Well, we're going to shift in some other zeros. So 0, 0. There is the result. So the result of this expression is 0, 0, 0, 0, 1, 1, 0, 0. There we go. And you shift in the zeros regardless of what the values in the front are. You always shift in zeros when you shift to the left. So why did we do this? Well, let's think about this for a moment. If I have 3 and I multiply it by 4, I get an answer of 12. Well, so my operand here is 3, and my result is 12. And so when I shift to the left, whenever I do a shift to the left like this, it's the same as multiplying by power of 2. So every time I shift to the left, I'm moving things over by one binary place, one power of 2. And so when I shift over once, I multiply by 2. When I shift over a second time, I multiply by 4. So in this case, I multiplied 3 times 4, and I got the answer of 12. So it's kind of a cute way to do some kind of multiplication without actually having to do multiplication. You're just shifting the value over a couple of different places. Okay, so keep that in mind. Keep in mind the fact that shifting to the left is the same as multiplying by powers of 2. Now let's come back to the shift to the right and see what happens. Okay, so let's take our unsigned car again here. Unsigned car. And let's say C equals, and I'm going to put in here the value of 12 because we know what the 12 looks like. It looks like 0, 0, 0, 0, 1, 1, 0, 0, right? That's what it is. And if I were to do something like Y equals C, and I'm going to shift to the right by 2 spots. Now, when I shift back to the right by 2 spots, what I get for this is the following. I get 1, 2, 3, 4, 5, 6, 7, 8. I'm going to put this one over here. I'm going to put this one right here. This is my 0, and this is my 0, and this is my 0, and this is my 0. These 2 bits go away. They get lost. And then I have these 2 empty locations over here. So what do I do with these empty locations? Okay, so here's the deal. If you're dealing with an unsigned value, then we're going to put zeros into these locations. So this is 0, 0, just like this. And the reason is because this shift to the right is the same as dividing by powers of 2. So when I shift to the right by 2 spots, I'm dividing by 2 and then 2 again, or dividing by 4. And notice we're going from 12 back to 3, right? This is 12 divided by 4 equals 3, and this gives us the correct result. And this is the reason we put the zeros in the front. Now, things change when we go to a signed value. So let's think about this as a signed car, or just a regular car, if you will. C equals 12. This, the same thing happens here. Nothing changes. Right? And when I shift to the right by 2 spots, I still get the 0, 0, 0, 0, 0, 1, 1. This is still 12 divided by 4 gives you 3. But things change if I'm dealing with something else. So let's think about a 4-bit signed number, for example, just to make it a little bit simpler. And let's think about what happens when I do -6 divided by 2. Right? -6 divided by 2, everyone knows is -3. Right? In order to get this, let's think about what -6 looks like. So +6 is this. So -6 is this number. There's -6 as a 4-bit 2's complement number. And now let's do a shift to the right by 1 spot, and let's see what we get. So when we shift this to the right by 1 spot, here's our 4 digits that we're going to have. And we will have the 1, 0, 1. This thing goes away. And then we have to figure out what to put here. Well, in this case, we need to put a 1 in here. And here's the reason why. Because this quantity right here is a 2's complement number is, in fact, -3. So this becomes 1, 1, 0, 0, and this is a +3. So this thing up here is a -3, which is the right answer, right? We want to get -3. But it only works if we put a 1 there. If we put a 0 there instead, we would get this quantity, which is equal to +5. That's clearly not the right answer, right? That's the wrong answer. We don't want a +5. So we need to make sure that this bit is a 1 and not a 0. So when you do a signed shift to the right, you are going to 1, 2, 3, 4. When I have this quantity up here, let's suppose it looks like this. 0, 1, 0, 1, 1. We know that this is a negative value because it has the leading 1 in front. And so we're going to take this leading value that is in the front, and that's the thing that we're going to shift in. So we're going to shift in copies of this, and then we can put the other digits into their right locations where we want them to be. So in this case, I'm doing a shift to the right by 3. So I put in, or I'm doing a shift to the right by 2, sorry. So I'm putting in 2 copies of this leading bit. So you put in copies of leading bit. When you do a signed shift to the right, you put in copies of the leading bit. If it was a negative number before, you have to keep it a negative number. If it was a positive number before, you have to keep it a positive number. So whatever that leading bit is, that's the value you're going to shift in. And this allows us to use shifting to do signed division, if you will, when we shift to the right. All right, so at this point, that's enough on the notepad. And now we're going to transition over to the computer. And we're going to see what this looks like in an actual C program.